Hi, this is Theorem. I'm studying in Institute of Aeronautical Engineering. I'm studying BTech first year Computer Science Engineering. Today we are going to discuss about unitary matrix pencils in signal processing. Okay. The fundamental problem or matrix in in signal processing can be solved by assumption. The easiest problem in matrix form of signal processing can be solved is sum of its exponentials. This problem is called retrieval of harmonics. The problem of retrieval of harmonics can be solved by taking its eigenvalues. Okay, today we are going to discuss these six subtopics in unitary matrix pencils in signal processing. Abstract introduction, unitary Heisenberg matrices, Scar parameter, error bounds, numerical examples, and conclusion. Abstract 3 to 4 pages, introduction 5 to 7 pages, unitary Heisenberg matrices, Scar parameter 8 to 13 pages, error bounds 14 to 16 pages, numerical examples 17 to 22 pages, conclusion 23 pages. We are going to see two numerical examples. Abstract. The problem of retrieval harmonics of a measured signal can be solved via solving an eigenvalue problem for an unitary Heisenberg matrix H built from square parameters of the Topoles matrix of signals autocorrelation concepts. From the eigenvalues E, I, K, we get the approximated frequencies K, and from the arched components of the corresponding eigenvectors, we get the amplitudes. The eigenvalue problem for H is equivalent to the eigenvalue problem for the unitary matrix pencil GOG called the square parameter pencil, the eigenvalues being the same for both problems. The advantage of working with this generalized eigenvalue problem instead of solving the standard eigenvalue problem for H lies in the sparsity of matrix pencil. GOG, the only non-zero entries being in fact the square parameters. Solving the retrieval of harmonics problem as a unitary eigenvalue problem also has the advantage that we can make use of the mathematically rich eigenvalue structure of unitary matrices. This allows in a particular to give bounds on the distance of the computed approximation to the frequencies to the actual frequencies. We present the we present such results and numerical examples showing the accuracy of the method and the effectiveness of the preparation result. Introduction. A fundamental problem in signal processing is the approximation of a discrete time signal by sum of its exponents. I already said before the index. The easiest problem in the matrix form is sum of its exponentials, i.e. sk pp sk rho p j equal to 1 j e minus ij minus k. Okay. K equal to 0, 1, 2, n minus 1. This problem is also known as the retrieval of harmonics. The retrieval of harmonics can be solved. The retrieval of harmonics problem can be solved by taking its eigenvalues or any other form. The frequencies and amplitudes are often determined as the terms. Okay, sigma j equal to 1 to p mod wj square into e power I theta into jk. That such that k equal to 0 to n minus 1. K belongs to k equal to anything. Match approximations of the first and autocorrelation lags. Tk equal to sigma minus infinity to infinity sj bar into sj minus k. Same k equal to 0 to n minus 1. The Topoles matrix inbuilt with this Tk is called autocorrelation matrix of order n, and the problem can thus be viewed as the problem of approximating the entries of the autocorrelation matrix Tn in a suitable way. Typically, such an approximation is constructed via solving a linear system Tnx equal to b, or via modifying Tn or singular Topoles matrix T belongs to T congruent to T similar to n in computing vector in its null space. The frequencies j and then computed from x or dot. It can be shown, however, that approximations can be retrieved from the solution of unitary eigenvalue problem. The basic observation is that any Hermitian positive denote Topoles matrix Tn of the dimension n has the Cholesky decomposition Tn equal to T naught into E1 h E1 comma h into rho to E1 so on h power n minus 1 rho E1 total whole power h into E1 h rho E1 comma h power n minus 1 rho E1, where h of rho is h from 1 to n minus 1. It is an n-unitary Heisenberg matrix in parameterized form, and the parameters fkg in f from k to g n 1 n belongs to 1 to n minus 1 are the square parameters from the Levinson algorithm applied to Tn is an arbitrary number on the unit circle. The frequencies J can essentially be computed from eigenvalue of such unitary Heisenberg matrix. The amplitudes J are given by the weights. Frequencies J is an amplitude and frequency both. The arched components of the corresponding eigenvectors normalized to a real value are non-negative. Thus, for the computation of the approximation, we can use the reliable and Asian eigenvalue methods available for unitary matrices. Unitary Heisenberg matrices are parameter. Any unitary n into n Heisenberg matrix H equal to H from gamma 1 to gamma n minus 1 to gamma n is the product of elementary reactors given by the parameters gamma k. H equal to G1 into gamma 1, G2 into gamma 2, and so on, Gn into gamma 1, where k equal to 1 to where k is the value can be taken from 1 to n minus 1. Gk into Gk brackets gamma k is equal to diagonal of ik minus 1 gamma matrix minus gamma k rho k gamma k bar gamma I n minus k minus 1 with sigma k belongs to R. Sigma k greater than or equal to 0. Gamma k whole square modulus of gamma k whole square plus sigma k whole square equal to 1. Modulus of gamma n modulus of gamma n is also equals to 1. And Gn into gamma n is equal to diagonal matrix of in minus 1 comma minus gamma n. Here ij denotes the j by j identity matrix and gamma k bar denotes the complex conjugate of gamma k. Gamma k is also a matrix. The parameters sigma k belongs to 1 to n minus 1 are called normalized complementary square parameters of H. See note that gk gamma k is uniquely determined then gamma k. In 2 we find that H equal to H in equation 2. This is the equation 2. H equal to H into first we have written that in the first statement. In that equation, we find that H equal to H into gamma 1 to gamma n minus 1 to gamma n can be transformed by unitary matrix Q to Q power H Q. Okay. Q power H Q equal to G naught G E power H, where G naught G E are the block diagonal unitary matrices with block size at most 2 of the following. G0 equal to G1 into gamma 1, G3 into gamma 3, and G5 into gamma 5, so on. G2 into modulus of n plus 1 by 2 minus 1 and gamma 2 modulus of same n plus 1 by 2 minus 1. The value of G and gamma are same. Ge power H equal to G2 gamma 2 and G4 gamma 4, G gamma 6. If you multiply, we will get the first equation H equal to H into gamma 1 to gamma n minus 1 to gamma n. Okay. where step of X equal to maximum of I belongs to Z or I less than or equal to X and I less than or equal to X. Thus, the eigenvalue problem for H is equivalent to the eigenvalue problem for the unitary matrix pencil G0 and Ge are called the square parameter pencil. The eigenvalues being the same for both problems and the eigenvectors being transformed into each other by Q. The advantage of working with this matrix pencil to solve the unitary eigenvalue problem is its sparsity. The only non-zero entries being in fact in the square parameters. When work with H, we have to think in terms of the n-fold matrix product, producing n into n minus 1 by 2 non-zero entries of H to develop and not understand the numerical methods. This make it harder to follow and understand the arguments to implement the algorithms. The relation between Toeplit's matrix of autocorrelation coefficients and the unitary Heisenberg matrix H allows us to compute the square parameter and the complementary square parameter directly from the signal by Asian isometric Arnoldi process applied to the downshift operator J. J is the frequency and amplitude, both we can consider it. The eigenvalues and weights of the corresponding square parameter pencil then also give the approximation to the signal frequencies and amplitude. Both frequency and amplitude is J, as the following theorem shows. Theorem 1. There are I think 3 theorems. Theorem 1. Let H equal to H1 H into gamma 1 gamma n 2 gamma n minus 1 gamma n. We already read it. Be unitary Heisenberg matrix. Let G0 minus lambda Ge be the square parameter pencil. built from the same square parameters gamma 1 to gamma n minus 1 gamma n and the related complementary square parameters. Then the matrix potential G naught minus lambda G has the same eigenvalues and weights as H. G naught minus lambda E is the square parameter pencil. This theorem states that the square parameter pencil and the matrix has same eigenvalues. From this equation, we see the first column of the transforming matrix Q in Q power H Q equal to G naught into G E power H is the first unit vector. The statement now follows immediately from studying the spectral decomposition of H and G naught G into G E power H. Thus, we may simply arrange the computer square parameters and complementary square parameters in the pencil form and solve this eigenvalue problem with the QR adaptation for unitary pencils instead of working with the unitary. This algorithm produces the same sequence of square parameters in each iteration as the unitary Q algorithm applied to the unitary Eisenberg matrix, as can be concluded from the following theorem. This is the second theorem, same as that one. Be unitary Eisenberg matrix and G naught minus lambda G with the square parameter pencil built from same square parameters and the related complementary square parameters. Lambda is a shift parameter which is not an eigenvalue, and H lambda is not an eigenvalue, it's a shift parameter, and perform one step of the QR algorithm with shift lambda on H and on G naught GE power H to create H cap and G dot cap and GE power H cap into respectively. Then H cap GUR as the same square parameters again. Okay, see that the unit vectors of H and G naught into G power H are created by the shift parameter lambda has same eigenvalues as H and G naught into GE power H. Proof. Investigating one step in pure algorithm for H and G naught into GE power H, we derive the statement with the analysis to the proof of theorem. Same proof is applied here. The proof is we need to calculate by QR algorithm. It is shown that one step of QR adaptation for the unitary matrix means G naught minus lambda G is completely equivalent to one step of the QR algorithm applied to G naught into G E over H if the same shift is used. Thus, we see from the theorem above that the QR adaptation for the unitary matrix pencil G naught minus lambda G can be considered as a direct way of computing the sequence of skull parameters that unitary QR algorithm would create for the unitary Eisenberg matrix H. Practical experience shows that QR adaptation from equation 4 means that we have derived in theorem 3 often gives results which have one more correct significant digit compared to the unitary QR algorithm. Error modes. Solving the retrieval harmonics via unitary eigenvalue theorem has also advantage that we make use of mathematically rich eigenvalue structure of unitary matrices. This allows in particular to give bounds on the distance of the computed approximations to the frequencies to the actual frequencies. The basic result is in the following. Theorem 3, let U belongs to C n by n be a unitary matrix. C be a unitary matrix of order n by n of order n, and Q1 belongs to C of order n with modulus of Q1 by modulus of Q2 equal to 1. Q1 belongs to C1, Q1 and Q2 belongs to C, Q1 by modulus of Q1 by Q2 equal to 1. I think Q1 equal to plus or minus Q2. Assume that n steps of the isometric analogy method applied to matrix U have produced the square parameters gamma 1 to gamma n and the corresponding complementary square parameters sigma 1 to sigma n. Let rho equal to gamma n by modulus of gamma n, and consider that unitary Eisenberg matrix H equal to H into gamma 1 to gamma n minus 1 and gamma n. In place of gamma n, he had taken that rho. Gamma means modulus of gamma n is equals to 1 or the corresponding square parameter pencil. If we denote eigenvalues of H or the square parameter pencil be by mu1 to mu n, and the eigenvalues of U by lambda 1 to lambda n, Then for I equal to 1 to n, minimum of modulus of mu minus lambda j less than or equal to root over sigma n square plus rho minus gamma n modulus of rho minus gamma n whole square. Moreover, there is a permutation 2 of 1 to n such that for each I belongs to 1 to k, mu I minus lambda to the second of I modulus less than is equal to root over sigma k square plus modulus of rho minus gamma k whole square. The first part of the theorem says that for each I on the unit circle, there is at least one eigenvalue of u, which is at most root over sigma n square plus modulus of rho minus gamma n whole square away. It's just the radius or distance from eigenvalue u to shift parameter lambda. Several mu's might still approximate the same in this way. The second part of the theorem, however, says that there is an argument of n eigenvalues of q which are separately approximated by the eigenvalues mu1 to mu n. Where is bound? The quality of the approximation mu I also depends on the magnitude of the last component Sn of the normalized eigenvectors of H or the corresponding square parameter pencil corresponding to eigenvalue mu I. Further investigation on the basics of theorem 3 leads to a result, say theorem 3. Theorem 4, with the notations above the following holds, minimum of j belongs to I to n same Sn modulus of Sn is added. What mu I minus lambda j less than or equal to modulus of S sin root over sigma n square plus modulus of rho minus gamma n whole square. The mu I as well as the lambda j are on the unit circle have therefore a representation as e power theta I congruent to e power theta ij power I theta I and e power I theta j respectively. Therefore, the bound above also goes a bound for the distance of the frequencies theta I bar and theta j. If we study theorem especially for q as the n by n downshift matrix j and for the normalized signal vectors is equal to s1 to sn as vector q1 and then theta I bar are the approximations to the desired frequencies derived with the method described in the beginning, and the theta j are the frequencies in an exact representation of the signal is equal to s1 to sn. And theorem 4 provides us with an estimate for the correctness of approximations of the form. The minimum value of minimum of theta modulus of theta I bar minus theta j less than or equal to across 2 minus sn modulus of sn all square into sigma n square plus modulus of gamma n. Again, root is cancelled with square. Modulus of rho minus gamma n whole square by 2 equal to a cos I. Numerical examples. There are one and this is the first example and this is the second example. We are going to do two numerical examples. As that we consider sk equal to this is the first numerical example. Sk equal to sigma l equal to 1 to 5 rho l e power I k theta l plus alpha vk, where vk is a random number which represents noise. Alpha belongs to r is a scalar, theta l equal to 2 pi ml by n, where ml is the 1 ml belongs to 1 to n, ml not equal to mj, I not equal to j, l not equal to j, for l not equal to j, l comma j belongs to 1 to 5. In each example, the signal vector s equal to s1 to sn power t is formed and 5 steps of the isometric Bernoulli method are applied to this. This yields the square parameter gamma 1 to gamma n, gamma 1, gamma 4, gamma 5 and the unitary upper Heisenberg matrix h5 equal to h5 gamma 1 to gamma 4 gamma 5 by modulus of gamma 5 are the square parameters or the corresponding square parameters pencil. For our discussion here we will consider Heisenberg matrices. The eigen decomposition of hy is completed. Estimates theta l bar and rho l bar are the frequencies and the amplitudes. Here f is replaced with theta l bar and rho l bar for this problem, and amplitudes are obtained from the eigenvalues. First, components of the eigenvectors respectively for each example actually minimal the distance of theta l to theta j. It's computed as well as the bound a cos for I equal to 1 to 5. As we do not know of an error bound for the amplitudes, we just compute the distance between rho l bar and rho l. As such example, we consider as k equal to 1.2 into e power 2 pi pi k by n plus 3.5 into e squared 2 pi k by n or something. For different values of alpha belongs to R, the frequencies are well separated. The following table lists and results for this example. The four sides of alpha are alpha equal to e minus 12, 1e minus 06, 1e minus 03, 1e minus 0 in this order. So the values, the last complementary square parameters of sigma phi are sigma phi equal to 1.9209 into e power 13, sigma phi equal to 1.7417 into e power 08, 1.721 into e power 2, 4.4414 into e power 1. In this order, for the four different cases, 1, E2, E3, E4, E5. Not subtracting means smaller the better equation, the better are the approximations of the frequencies are much better than the upper bounds indicate. For small perturbations, the upper bounds cause I overestimate the approximation error by several powers of 10. The method seems to approximate amplitudes with about same accuracy as the frequencies. In practice, of course, we would not know exact value of n. The number of frequencies and amplitudes need to compress the signal as a sum of exponentials. The above results indicate that a rule of thumb could be to let Arnoldi method run until sigma j is obtained, which is smaller than the some gives tolerance, some given tolerance. The quality of the approximations depends on sigma j, the largest permutations observed percentage of sigma. This is the second example, same as that one. In this second example, we have sigma phi values as 6.619 into e power 14. Four different cases we will calculate it. Conclusion: this method has difficulties to approximate for the first two frequencies and amplitudes. Okay, the results for these approximations have been better in the previous example, where the first two frequencies and amplitudes are much better separated. The actual approximations error for the first two frequencies are only the order estimate. Thank you for listening.